Moving fluid at this scale requires managing extreme mass. The core engineering objective is capturing and transferring 625 cubic meters of water every single hour. That volume must be driven against a total head of 250 meters, a vertical lift requirement that dictates the entire structural design of the facility. This wireframe maps the subterranean structure. Below the surface sits an 8-meter diameter, 16.5-meter deep circular concrete jackwell. The pump's static resting weight is immense, but active dynamic loads from pulling water upward require this thick concrete envelope to absorb the kinetic stress. Sitting directly above that concrete abyss is the industrial pump floor, constructed from 10-millimeter thick mild steel checkered plates and supported by heavy steel eye girders. The plates feature a stamped diamond pattern. In an environment with constant high-pressure water movement, keeping the surface anti-slip is a mandatory safety requirement. Before any water travels upward, this structural bedrock must be perfectly secured to prevent the operating pump's dynamic forces from tearing the station apart. At the very bottom of the 16.5-meter drop sits the lowest intake point of the system, the FG260 suction bell. This diagram illustrates the engineered bell mouth shape. The flared curve directs fluid vectors smoothly into the intake, minimizing friction. Removing that precise geometry causes water to tear into the inlet, creating cavitation, destructive vapor bubbles. The bell mathematically prevents these bubbles. Directly above that protective bell sits the hydraulic engine of the system, the multi-stage bowl assembly. Inside these bowls, cast iron outer casings pair precisely with bronze or stainless steel impellers. This material synergy reduces internal friction to preserve fluid momentum. This step chart tracks internal pressure. A single impeller cannot generate enough lift. Instead, fluid is driven through stacked stages, sequentially compounding hydraulic pressure. Clearing the final stage, the total pump head reaches 250 meters, locking in an 82% bowl efficiency. The impellers solve the hydraulic lift problem. The next challenge is bridging a 16.5-meter vertical gap to deliver the raw mechanical power required to spin. Spanning that 16.5-meter vertical drop is the primary mechanical artery of the pump, a hollow line shaft forged from stainless steel 431. Because a single shaft of that length would be impossible to transport or install, it is assembled from individual precision sections, locked together using heavy-duty threaded couplings. Delivering 650 kilowatts of mechanical energy straight down a 16.5-meter column generates immense torsional force. To keep the shaft bearings from burning up, they are externally lubricated entirely by a thin layer of the pumped water itself. Relying on fluid lubrication eliminates the need to run complex, heavily pressurized oil lines deep underwater, stripping away a major potential failure point. Surrounding this spinning shaft are thick, mild steel column pipes. These act as the rigid structural hanger holding the weight of the multi-stage bowls below. As the pumped water travels upward inside these pipes, its velocity is strictly limited by the pipe diameter to a maximum of 2.5 meters per second. Pushing fluid faster than that threshold introduces severe friction loss against the steel walls and triggers destructive mechanical vibration. The column pipe architecture is a carefully balanced compromise. It acts simultaneously as an unbending, load-bearing hanger and a highly optimized conduit for fluid delivery. Back up at floor level sits the fabricated carbon steel surface discharge head. This piece of hardware executes two specific geometric functions. It takes the vertical column of pressurized water and turns it exactly 90 degrees horizontally, while bearing the entire static weight of the motor mounted above it. Right at this right-angle junction is a tightly calibrated bronze and stainless steel stuffing box. Adjustable glands compress packing material against the spinning shaft, preventing high-pressure water from leaking upward. Simultaneously, pushing the massive water column generates intense downward hydraulic thrust. A heavy-duty thrust bearing captures this energy, safely dispersing it into the floor girders. Without the thrust bearing absorbing that specific vertical load, the downward pull on the shaft would instantly crush the motor's internal electrical components. This discharge head and bearing assembly acts as the physical firewall of the entire system. It isolates the highly pressurized hydraulic environment below from the sensitive electrical drive above. The prime mover of this system is lowered into position by a 10-ton electric overhead traveling crane, descending from a 10-meter ceiling. The prime mover itself is a high-tension electric motor rated at 650 kilowatts, operating at 6.6 kilovolts. Running at 50 Hz, the motor spins the shaft at a maximum speed of 1480 RPM, achieving an electrical efficiency of 93.5%. Processing that much high-tension power requires continuous telemetry. Small cylindrical vibration transmitters are mounted to the motor surface, paired with embedded temperature sensors monitoring the internal copper windings and bearings. Driving this hardware are thick power cables that route back to 6.6 kilovolt FCMA soft starter panels, giving operators precise control over the voltage ramp-up. This logic tree maps automated trip protocols. If water level hits a low state, logic triggers a system trip, preventing a dry run. This kill switch monitors telemetry. If moisture enters, windings overheat, or pressure falls outside safe ranges, the system automatically shuts down. Generating massive rotational torque is only possible with a sub-second automated nervous system capable of instantly killing that power to prevent self-destruction. Once the water is forced through the surface discharge head, it enters a thick horizontal steel delivery pipe. The fluid velocity here drops to 2.0 meters per second, moving through an interior coated in food-grade epoxy to prevent steel degradation. Attached to each individual pipe is a specific sequence of industrial hardware. First is an automatic air inlet and release valve, which vents trapped air to prevent vacuum collapse and airlocks. Next in line is a slanted disc swing check valve. If the facility loses power, 250 meters of vertical water will immediately attempt to reverse direction. This non-return valve slams shut, physically blocking that high-pressure backflow from reversing into the pump and shearing the internal shaft. Downstream from the check valve is an electromagnetic flow meter, followed by a motorized double eccentric butterfly valve. Coated in electrostatic epoxy powder, this butterfly valve carries a PN40 pressure rating. A top-mounted actuator gear mechanism automatically modulates the output flow. The final component in this schematic is a set of stainless steel corrugated expansion bellows. These accordion-like rings act as a mechanical buffer, compressing under load to fully decouple motor vibrations and intense thermal expansion away from the rigid common delivery header. This 80% overall efficiency is a direct result of meticulous management. The system tames its own destructive byproducts across the hydraulic, structural, and electrical domains, while maintaining its core output.